In the next 30 seconds, somewhere in our galaxy, a chunk of matter the size of a sugar cube will weigh more than Mount Everest. Right now, as you read this sentence, there is an object spinning so fast its equator moves at 150,000 kilometers per second, yet it maintains perfect timing accuracy for millions of years. We call these impossibilities neutron stars, and they shouldn't be able to exist. Everything we thought we knew about matter was wrong. We learned in school that atoms are mostly empty space, vast distances between tiny nuclei and orbiting electrons. We believed that solid objects could only be compressed so much before molecular bonds break and materials crumble. We assumed that the densest substances on Earth, osmium, uranium, platinum, represented the limits of how tightly matter could be packed. Then, we discovered stellar corpses where the empty space simply disappears. Picture this. Take every human being who has ever lived, roughly 100 billion people throughout history, and crush them all into a volume smaller than a marble. That marble would still be 1,000,000 times less dense than the matter inside a neutron star. These objects contain 500 times more mass than Earth compressed into spheres you could fit inside most major cities. The physics governing these stellar remnants operates by rules so extreme they seem like violations of natural law rather than expressions of it. Surface gravity, 200 billion times stronger than Earth's. Magnetic fields that will be lethal at the distance of the moon. Temperatures that make the core of the sun seem cool by comparison. And through it all, clockwork precision that puts our most accurate timepieces to shame. But here is what makes neutron stars truly unsettling. They represent what happens when the universe as fundamental forces reach their breaking point. These aren't just dense objects. They read demonstrations of what occurs when gravity becomes so powerful it can overwhelm the electromagnetic forces holding atoms together, crushing matter beyond recognition into forms that exist nowhere else in the cosmos. Dr. Robert Oppenheimer first predicted these impossible objects in 1939, calculating that stellar cores containing more than 1.4 solar masses would collapse to densities where neutrons themselves get pressed together like marbles in a jar. His equations suggested the existence of matter so dense it would warp space and time around it, creating gravitational fields intense enough to bend light and slow time itself. For 3 decades, neutron stars remained theoretical curiosities that most astronomers assumed would never be detected. Then graduate student Jocelyn Bell Burnell noticed strange regular signals pulsing from space with mechanical precision. The signals repeated every 1.337 seconds without variation, leading researchers to briefly consider extraterrestrial intelligence as a possible explanation. What Bell Burnell had actually discovered was something far stranger than alien communications. A stellar remnant spinning once every 1.337 seconds while sweeping beams of radiation across space like a cosmic lighthouse. The Crab pulsar, formed by a supernova witnessed by Chinese astronomers nearly 1,000 years ago, was broadcasting its existence through pure physics, demonstrating that nature could create objects whose very existence challenges our understanding of what matter can become. These discoveries revealed that our universe contains objects operating at the intersection of quantum mechanics and general relativity, where the smallest scales of physics merge with cosmic phenomena spanning thousands of light years. Neutron stars exist in a regime where everyday intuitions about matter, gravity, and time break down completely. Consider that the calcium in your bones, the iron in your blood, the gold in your jewelry, all of it was forged in processes connected to neutron star formation. When massive stars explode to create these dense remnants, they scatter heavy elements throughout space. When neutron stars collide, they forge elements heavier than iron through nuclear processes impossible to replicate in any terrestrial laboratory. Tonight, we are going to explore how nature creates objects so dense they make black holes seem simple by comparison. We'll discover what happens when stellar cores undergo gravitational collapse so violent it obliterates atomic structure in less than a second. We'll uncover why these cosmic timekeepers pulse with mathematical precision while generating magnetic fields that would restructure matter at the molecular level. And we'll reveal how studying these impossible objects is rewriting our understanding of matter, gravity, and the fundamental limits of physical reality. From the quantum mechanical processes governing superfluid neutron cores to the gravitational wave signals produced when these stellar monsters collide, neutron stars operate as natural laboratories where physics reaches its most extreme expressions. If you're fascinated by impossible physics and cosmic mysteries that shouldn't exist, subscribe and hit thumbs up. And here is something that will blow your mind. If you could compress Earth to neutron star density, how small would our planet become? Comment your answer below. I'll pin the most creative calculation. What we're about to discover will fundamentally change how you think about matter, density, and the hidden violence that shapes our cosmos. Every atom in your body has been processed through cosmic furnaces operating under conditions that push the laws of physics beyond their apparent breaking points. You're not just learning about distant astronomical objects. You're re-exploring the extreme processes that made your existence possible. The story of neutron stars is the story of matter under siege by gravity, where normal physics surrenders to quantum effects operating on astronomical scales. It's a tale of stellar death that becomes cosmic rebirth, where the most violent explosions in nature create the most precise phenomena in the universe. These stellar remnants exist at the boundary between matter and something beyond matter, where our familiar concepts of atoms, molecules, and chemical bonds dissolve into quantum states that have no terrestrial analogs. They demonstrate that the universe is far stranger and more extreme than our earthbound experience suggests. Now let's begin our journey into the heart of impossibility itself, where atoms die, and physics is reborn in forms that challenge everything we thought we knew about the nature of reality. Chapter 1. Stellar Death. When you look up at the night sky, you're seeing stars in their prime. Massive fusion reactors burning bright against the darkness. But hidden among those points of light are stellar corpses so dense and strange, they redefine what we mean by matter itself. To understand why neutron stars are the densest objects in the universe, we first need to witness how ordinary stars die the most extraordinary deaths. Our journey begins with stars at least 8 times more massive than our Sun. These stellar giants live fast and die young, burning through their nuclear fuel in just millions of years compared to our Sun's 10 billion-year lifespan. But it is not the speed of their lives that matters. It is the violence of their deaths. Throughout their lives, massive stars wage a constant battle against their own gravity. In their cores, nuclear fusion creates outward pressure that balances the inward pull of their immense mass. For millions of years, this cosmic tug-of-war maintains a delicate equilibrium. The star burns hydrogen into helium, then helium into carbon, then carbon into neon, oxygen, and finally silicon. Each fusion process happens faster and at higher temperatures than the last, like a stellar timer counting down to an inevitable explosion. The end comes when the star's core begins fusing silicon into iron. This marks the beginning of the end, because iron is where fusion stops being profitable. Unlike lighter elements, iron fusion consumes more energy than it produces. When the core fills with iron, the star has perhaps seconds left to live. What happens next defies comprehension. The core temperature reaches 100 billion degrees, 6,000 times hotter than the Sun's core. At these temperatures, iron nuclei begin breaking apart, absorbing vast amounts of energy. Simultaneously, electrons get crushed into protons, creating neutrons and releasing ghostly particles called neutrinos. The core pressure drops catastrophically. In less than a second, the stellar core collapses from the size of Earth to the size of Manhattan. The material falls inward at 30,000 miles per second, 10% the speed of light. When this collapsing matter hits the incredibly dense neutron core that forms at the center, it rebounds like a cosmic sledgehammer hitting an anvil. The rebound creates a shock wave that races outward through the star at 10,000 miles per second. This shock wave rips through the star's outer layers, heating them to billions of degrees and blasting them into space in what we call a supernova explosion. For weeks, this single dying star can outshine an entire galaxy of 100 billion stars. But the real story is what's left behind. In the center of this cosmic violence, crushed by pressures beyond imagination, the star's core has undergone a transformation that creates the densest form of stable matter in the universe. Protons and electrons, the basic building blocks of ordinary atoms, have been squeezed together so forcefully they've merged into neutrons. To appreciate how extreme this compression is, consider that a typical atomic nucleus occupies only 1/1,000,000th of an atom's volume. The rest is empty space between the nucleus and orbiting electrons. In a neutron star, this empty space simply ceases to exist. The neutrons pack together like balls in a box, with no gaps between them. The result is matter compressed to nuclear density, roughly 500 million tons per cubic centimeter. At this density, all the people on Earth could be compressed into a volume the size of a sugar cube. A neutron star contains about 1.4 times the mass of our Sun crushed into a sphere just 12 miles across. To put this in perspective, you could fit about 50 neutron stars across the width of most major cities. This compression is so extreme it bends space and time around the neutron star. The surface gravity is 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, you would weigh as much as Mount Everest. A paper clip would weigh as much as a cruise ship. The gravitational field is so intense that light itself struggles to escape, causing the star to appear dimmer than its temperature would suggest. Dr. Robert Oppenheimer and his student, George Volkoff, first predicted neutron stars in 1939, just 2 years after neutrons themselves were discovered. They calculated that if a stellar core contained more than about 1.4 solar masses, now called the Chandrasekhar limit after physicist Subrahmanyan Chandrasekhar, no force in nature could prevent gravitational collapse to densities where neutrons touched. For nearly 30 years, neutron stars remained theoretical curiosities. Astronomers had no way to detect objects so small and dense. Then, in 1967, graduate student Jocelyn Bell Burnell noticed strange, regular radio signals while analyzing data from a new radio telescope at Cambridge University. The signals pulsed every 1.337 seconds with clockwork precision, leading the research team to initially consider the possibility of alien communications. What Bell Burnell had actually discovered was something far stranger than aliens: a neutron star spinning once every 1.337 seconds, sweeping beams of radio waves across space like a cosmic lighthouse. As the star rotated, its magnetic field, 1,000,000,000,000 times stronger than Earth's, accelerated particles to nearly the speed of light, creating intense beams of radiation that we detect as pulses when they point toward Earth. This discovery revolutionized astronomy and confirmed one of the most extreme predictions of physics. Here was direct evidence of matter compressed beyond the density of atomic nuclei, spinning with the precision of atomic clocks while generating magnetic fields that would instantly kill any living thing within 1,000 miles. The Crab pulsar, formed by a supernova observed by Chinese astronomers in 1054 AD, spins 30 times per second and has been slowing down at a rate of 38 nanoseconds per day for nearly 1,000 years. This incredible regularity allows astronomers to use pulsars as cosmic clocks, detecting gravitational waves and testing Einstein's theories with unprecedented precision. But neutron stars represent more than just extreme physics demonstrations. They're the universe's recycling centers, taking the heavy elements forged in stellar cores and distributing them throughout space. When neutron stars collide, an event so violent it creates gravitational waves detectable across billions of light years. They forge elements heavier than iron and scatter them across the cosmos. The story of neutron stars is ultimately the story of how matter behaves when pushed to its absolute limits. These stellar remnants exist at the boundary between ordinary matter and something beyond our everyday experience. They show us that the universe is far stranger and more extreme than our earthbound intuitions suggest. As we'll discover in our next chapter, the density of neutron stars isn't just a number. It has a window into physics regimes impossible to study anywhere else, where the very nature of matter transforms into something almost unrecognizable. Chapter 2. Nuclear Density. Imagine taking every car on Earth, roughly 1 billion vehicles, and crushing them all into the volume of a single raindrop. The resulting density would still be 1,000,000 times less than the matter inside a neutron star. We're about to explore densities so extreme they challenge our understanding of what matter actually is. To grasp neutron star density, we need to zoom into the heart of ordinary atoms. Picture the nucleus of a hydrogen atom as a marble sitting in the center of a football stadium. The electron orbiting this nucleus would be smaller than a grain of sand, circling somewhere in the bleachers. Everything between the marble and the grain of sand, essentially the entire stadium, is empty space. This emptiness defines normal matter. Your hand, seemingly solid, is actually 99.9999999% empty space. The atoms in your body are like solar systems, with tiny nuclei separated by relatively vast distances. Even in the densest materials on Earth, osmium, platinum, or uranium, atoms remain mostly empty space, held apart by electromagnetic forces. Nuclear density represents what happens when this empty space gets eliminated entirely. Inside a neutron star, matter reaches densities of 500 million to 1 billion tons per cubic centimeter. At these densities, atomic structure as we know it simply cannot exist. The electromagnetic forces that keep atoms intact become overwhelmed by gravitational pressure, so intense it fundamentally transforms matter itself. The transformation begins during the final moments of stellar core collapse. As temperatures soar beyond 100 billion degrees and pressures exceed anything found elsewhere in the universe, protons and electrons, the fundamental building blocks of atoms, get squeezed together with such violence they merge into neutrons. This process, called neutronization, destroys the very concept of atomic structure. Dr. Lev Landau first described this process in 1932, shortly after the neutron was discovered. He realized that under extreme gravitational pressure, the electromagnetic forces holding atoms together would be overpowered, allowing protons and electrons to combine. The resulting neutrons could then be packed together at nuclear density, the same density found inside atomic nuclei, but extended throughout an entire star. To appreciate how extreme nuclear density is, consider this comparison. If you could compress Earth to neutron star density, our entire planet would shrink to a sphere just 300 meters across, smaller than the length of 3 football fields. Yet this tiny sphere would contain all of Earth's mass. Every mountain, every ocean, every grain of sand, compressed into a volume you could walk across in a few minutes. The physics governing matter at nuclear density operates by completely different rules than ordinary matter. Neutrons, having no electric charge, can be packed together far more tightly than atoms ever could. They're held together not by electromagnetic forces, but by the strong nuclear force, the same force that binds protons and neutrons inside atomic nuclei. At these densities, neutrons behave more like a quantum fluid than individual particles. They form what physicists call a degenerate neutron gas, where quantum mechanical effects become the dominant force preventing further collapse. The neutrons exist in the lowest possible energy states, packed together so tightly they resist further compression through quantum pressure alone. Recent observations from the neutron-star interior composition explorer, NICER, aboard the International Space Station have revealed just how strange matter becomes at these densities. NICER measurements of pulsar PSR J0030+0451 show that neutron star matter is so stiff, so resistant to compression, that these stars are larger than previously thought, with radii around 13 kilometers despite containing 1.4 solar masses. This stiffness suggests that neutron star cores might contain exotic forms of matter that don't exist anywhere else in the universe. At the very center, where densities exceed even nuclear density, neutrons themselves might break down into their constituent quarks, forming a quark soup unlike anything we can create in particle accelerators on Earth. The transition from ordinary matter to neutron star matter doesn't happen gradually. Computer simulations show that during core collapse, the density increases by a factor of 100 trillion in less than a second. One moment, you have iron nuclei separated by relatively vast atomic distances. The next moment, you have a sea of neutrons packed together at nuclear density. This phase transition is so violent, it would be like taking every grain of sand on all of Earth's beaches and compressing them into a space the size of a city block. Except instead of sand grains, we're compressing atomic nuclei, and instead of a city block, we're creating matter denser than the nucleus of an atom. Dr. Norman Ramsey, who won the Nobel Prize for his precision measurements of atomic properties, once calculated that a single teaspoon of neutron star material would weigh about 6 billion tons on Earth. This is roughly equivalent to the mass of Mount Everest compressed into a volume you could hold in your hand. But neutron star density isn't uniform throughout the star. Like an onion, neutron stars have layers with different compositions and densities. The outer crust consists of heavy atomic nuclei in a sea of electrons, with densities similar to white dwarf stars. Deeper down, as density increases, these nuclei become so neutron-rich they begin to drip neutrons, creating increasingly exotic forms of matter. In the inner crust, neutrons become superfluid, flowing without friction in a state similar to liquid helium at absolute zero. The protons in this region form a superconductor, carrying electric current without resistance. These quantum states can only exist at temperatures near absolute zero and pressures that dwarf anything achievable on Earth. At the core, where densities may exceed 10 times nuclear density, matter might transform into something we can barely comprehend. Theoretical physicists propose the existence of Hyperion matter, where neutrons and protons are joined by strange particles containing quarks not found in normal matter. Some models even suggest the formation of quark matter, where the familiar particles we know dissolve into their fundamental constituents. The European Space Agency SX Mem-Newton Observatory has detected neutron stars with surface temperatures of 1 million degrees, hot enough that thermal X-rays escape despite the star's intense gravitational field. These observations confirm that neutron star matter conducts heat with extraordinary efficiency, suggesting crystalline structures in the outer layers where nuclei form regular lattice in the electron sea. Understanding neutron star density isn't just an academic exercise. These extreme environments serve as natural laboratories for studying matter under conditions impossible to recreate on Earth. The densities inside neutron stars exceed what we can achieve in particle accelerators by factors of trillions. Every measurement we make of neutron star properties, their masses, radii, temperatures, and magnetic fields, provides clues about how matter behaves at nuclear density. These observations constrain our models of quantum chromodynamics, the theory describing the strong nuclear force, and help us understand the fundamental properties of matter itself. As we'll discover next, This extreme density creates gravitational fields so intense they warp space and time in ways that would seem impossible if we hadn't detected them directly. Chapter 3. Gravitational Extremes. Standing on the surface of a neutron star, you would experience gravity so intense that your body would be stretched into a thin stream of atoms before you could complete a single thought. The gravitational field at a neutron star's surface is 200 billion times stronger than Earth's. So extreme, it warps the very fabric of space and time into shapes that defy human intuition. To understand how gravity becomes this overwhelming, we need to appreciate how mass and distance interact in Einstein's equations. Gravity isn't just about how much mass an object contains. It is about how tightly that mass is packed together. Earth's gravity comes from 6 times y kilograms of mass spread throughout a sphere 12,756 kilometers wide. A neutron star contains 20% more mass compressed into a sphere just 24 kilometers across. This compression amplifies gravitational effects by astronomical proportions. Since gravitational force increases with the square of distance reduction, compressing the Sun's mass from 1.4 million kilometers diameter down to 24 kilometers increases surface gravity by a factor of nearly 4 billion. The result is a gravitational field so intense it approaches the theoretical limits of what matter can withstand. Dr. Carl Schwarzschild first calculated these extreme gravitational effects in 1916. Just months after Einstein published his theory of general relativity. Schwarzschild showed that there is a critical radius, now called the Schwarzschild radius, where gravitational effects become so extreme that nothing, not even light, can escape. For a 1.4 solar mass object, this radius is just 4 kilometers. Neutron stars exist right at the edge of this gravitational abyss. With radii of 10 to 15 kilometers containing 1.4 solar masses, they're only 2 to 3 times larger than their Schwarzschild radius. This proximity to gravitational collapse creates effects so extreme they seem like violations of physics rather than natural phenomena. Consider what happens to time itself near a neutron star. According to Einstein's theory, gravity doesn't just bend space, it slows time. Near a neutron star's surface, time runs approximately 30% slower than it does on Earth. This means that if you could somehow observe someone standing on a neutron star, you would see them moving in slow motion, their clock ticking at 2/3 normal speed. This time dilation effect has been directly measured using neutron star observations. The gravitational effects extend far beyond simple time dilation. Light itself struggles to escape from neutron star surfaces. Photons leaving the surface lose significant energy climbing out of the gravitational well, causing neutron stars to appear dimmer and redder than their actual surface temperature would suggest. This gravitational redshift can make a white-hot neutron star appear merely red-hot to distant observers. NASA's Rossi X-ray Timing Explorer discovered even stranger gravitational effects around neutron star 4U1820-30. X-ray emissions from materials spiraling into this neutron star showed periodic variations that could only be explained by frame dragging, the neutron star's rotation literally twisting space-time around it like honey being stirred by a spoon. Frame dragging, predicted by Einstein, but only recently confirmed, demonstrates how massive spinning objects drag space-time along with their rotation. Near a rapidly spinning neutron star, space itself rotates. An object trying to orbit in the opposite direction would find itself fighting against the rotation of space-time itself. The surface gravity of a typical neutron star equals 200 billion times Earth's gravity. At this intensity, a 150-pound person would weigh 30 billion tons, equivalent to the mass of Mount Everest. The gravitational acceleration is so extreme that an object dropped from a height of 1 meter would impact the surface traveling at 2,000 kilometers per second. nearly 1% the speed of light. This extreme gravity creates a phenomenon called gravitational lensing on scales impossible around normal stars. Light rays from the far side of a neutron star get bent by its gravity and become visible to observers on the near side. This allows astronomers to see more than half of the neutron star's surface simultaneously, despite being spherical objects. The Neutron Star Interior Composition Explorer, NICER, uses this gravitational lensing effect to map neutron star surfaces with unprecedented precision. By measuring how much of the star's surface becomes visible due to light bending, NICER can determine neutron star radii to within a few hundred meters across distances of thousands of light years. Perhaps most remarkably, neutron star gravity is so intense it affects the star's own rotation. As neutron stars spin down over millions of years, their intense magnetic fields convert rotational energy into radiation. But the space-time curvature around spinning neutron stars creates additional effects that influence this energy loss in ways still being studied by theoretical physicists. The Laser Interferometer Gravitational Wave Observatory, LIGO, has detected gravitational waves from neutron star collisions, providing direct evidence of how these extreme gravitational fields behave during the most violent events in the universe. When two neutron stars spiral into each other, their gravitational fields create ripples in space-time itself that travel at light speed across billions of light years. These gravitational wave detections reveal that neutron star mergers involve gravitational energies equivalent to converting several % of the Sun's mass directly into pure energy. The collision GW170817, detected by LIGO in 2017, released more energy in gravitational waves during its final seconds than all the stars in the observable universe emit as light. But neutron star gravity creates challenges for our understanding of physics itself. The no-hair theorem suggests that black holes can be completely described by just three properties: mass, electric charge, and angular momentum. Neutron stars, existing so close to their Schwarzschild radius, challenge this simplicity by exhibiting complex magnetic fields, crystalline crusts, and internal structures that somehow resist gravitational homogenization. Recent computer simulations by Dr. Matthew Duez at Washington State University show that neutron star mergers create conditions where general relativity breaks down at the quantum level. In the final milliseconds before two neutron stars collide, gravitational fields become so intense that space-time itself might undergo phase transitions, similar to matter changing from liquid to gas. The gravitational environment around neutron stars serves as a natural laboratory for testing. Einstein's this theory under conditions impossible to replicate artificially. Every precise timing measurement of pulsar signals provides a test of general relativity in regimes where gravitational effects dominate all other forces. As neutron stars age and spin down, their gravitational fields remain constant while their rotational effects diminish. This allows astronomers to study how gravity behaves in isolation from other extreme effects. The most precisely timed pulsars serve as gravitational wave detectors, using their clockwork regularity to detect ripples in space-time caused by distant cosmic collisions. Understanding neutron star gravity isn't just about testing physics theories. These extreme gravitational fields explain how neutron stars serve as cosmic particle accelerators, generating the highest energy radiation we observe in the universe. They also explain how neutron star collisions can overcome gravitational binding and scatter heavy elements across space. The story of neutron star gravity reveals nature operating at the extremes of physical law. Where space and time bend into shapes our everyday experience cannot prepare us to understand. But as we'll see next, this extreme gravity enables another impossible phenomenon: magnetic fields so intense they would instantly restructure any atom that came near them. Chapter 4: Magnetic Monsters. The The magnetic field around a neutron star is so powerful it would be lethal at the distance of the Moon. These stellar remnants generate magnetic fields trillions of times stronger than Earth's, creating conditions where the very nature of matter and energy transforms into something unrecognizable. To understand how neutron stars achieve such magnetic extremes, we need to explore what happens when the universe's strongest magnets meet its densest matter. Earth's magnetic field, generated by molten iron circulating in our planet's core, reaches about half a Gauss at the surface. This seemingly weak field is strong enough to deflect cosmic radiation and guide compass needles across continents. Hospital MRI machines operate at around 30,000 Gauss, powerful enough to rip ferromagnetic objects across rooms and erase credit card magnetic strips. Neutron star magnetic fields dwarf these terrestrial examples by factors that strain comprehension. Typical neutron stars generate surface magnetic fields of 100 million to 1 trillion Gauss. The strongest magnetic neutron stars, called magnetars, reach field strengths of 1,000 trillion Gauss, powerful enough to strip electrons from atoms at distances of thousands of kilometers. The origin of these extreme magnetic fields lies in the violent process of stellar core collapse. When a massive star's core implodes during a supernova, any magnetic field present gets concentrated along with the matter. Since magnetic field strength increases with the square of compression ratio, the collapse from Earth-sized core to city-sized neutron star amplifies magnetic fields by factors of billions. Dr. Robert Duncan at the University of Texas first calculated how stellar collapse could create such extreme magnetic fields in the 1990s. His model showed that during core collapse, magnetic field lines get twisted and compressed like rubber bands being wound tighter and tighter. The final result is a magnetic field so intense it stores more energy than the sun produces in a million years. This magnetic field concentration doesn't occur uniformly. Computer simulations reveal that neutron star magnetic fields have complex, twisted structures extending from the stellar interior through the magnetosphere into surrounding space. These field lines act like cosmic superhighways, channeling charged particles at velocities approaching light speed and creating the beams of radiation we detect as pulsar signals. The interaction between matter and such extreme magnetic fields creates phenomena impossible anywhere else in the universe. In magnetic fields exceeding 100 million Gauss, atomic structure itself begins to change. Electron orbits become elongated into cigar-shaped configurations aligned with magnetic field lines. Atoms transform from spherical to cylindrical shapes, fundamentally altering their chemical and physical properties. At magnetar strength fields approaching 1,000 trillion Gauss, quantum mechanical effects dominate atomic behavior. The magnetic energy becomes comparable to atomic binding energies, essentially rewriting the rules of chemistry. Hydrogen atoms stretch into needle-like structures hundreds of times longer than they are wide. Heavier elements undergo transitions to magnetic quantum states that don't exist under normal conditions. NASA's Swift Gamma-ray Burst mission detected the most powerful magnetic field explosion ever observed from magnetar SKR 1806-20 on December 27, 2004. This stellar explosion, lasting just 0.2 seconds, released more energy than our sun produces in 250,000 years. The burst temporarily disrupted radio communications on Earth, despite originating 50,000 light-years away. The explosion occurred when magnetic stress in the neutron star S-crust exceeded the structural strength of matter compressed to nuclear density. When the crust finally cracked under magnetic pressure, stored magnetic energy equivalent to 1 trillion hydrogen bombs was released instantaneously. The resulting gamma-ray burst was so intense it temporarily blinded X-ray satellites throughout the solar system. These extreme magnetic fields explain one of neutron stars' most remarkable properties. their ability to generate precisely timed radio pulses. As neutron stars rotate, their magnetic field lines sweep through surrounding space like lighthouse beams. Charged particles trapped along these field lines get accelerated to nearly light speed, creating intense beams of radiation that we detect as pulses when they point toward Earth. The Arecibo Observatory, before its collapse in 2020, discovered neutron stars spinning over 700 times per second while maintaining magnetic fields strong enough to power lighthouse beams visible across thousands of light years. The fastest known pulsar, PSRJ 1748-2446 AD, completes 716 rotations every second while generating magnetic fields that would strip electrons from any approaching matter. Dr. Krissa Cavallo-II's team, using the Compton Gamma Ray Observatory, identified magnetars as a distinct class of neutron stars in the 1990s by observing their characteristic soft gamma repeaters, periodic bursts of high-energy radiation caused by magnetic field instabilities. These observations revealed that some neutron stars possess magnetic fields up to 1,000 times stronger than typical pulsars. The magnetic field strength around neutron stars creates effects that seem to violate conservation of energy. When charged particles spiral along magnetic field lines approaching the neutron star surface, they radiate away energy so rapidly they should quickly lose speed and fall into the star. Yet observations show steady particle acceleration continuing for millions of years. The solution to this apparent paradox lies in magnetic reconnection events, where tangled magnetic field lines snap and recombine, releasing stored magnetic energy that re-accelerates particles. These reconnection events occur continuously around neutron stars, maintaining the high-energy particle populations responsible for pulsar radiation despite energy losses that should deplete them in hours. Neutron star magnetic fields also interact with surrounding space in ways that reshape entire stellar neighborhoods. The magnetosphere around pulsar PSR B1259-63 extends so far into space it disrupts the stellar wind from its companion star, creating shock waves and particle acceleration regions detectable by radio telescopes on Earth. Perhaps most remarkably, neutron star magnetic fields can exist in states of superconduction that persist for millions of years without energy loss. The neutron star's interior contains superconducting protons that carry electric current without resistance, maintaining magnetic fields that would decay in ordinary matter within seconds. Recent observations from the Nuclear Spectroscopic Telescope Array (NuSTAR) have revealed magnetar magnetic fields undergoing gradual decay over astronomical timescales. Magnetar 1E2-259 plus 586 showed a magnetic field decrease of about 1% over 10. YEARS still extremely slow by human standards, but rapid enough to study magnetic field evolution in real time. These magnetic field measurements constrain our understanding of neutron star internal structure. The relationship between magnetic field strength and neutron star rotation rate provides clues about how superfluid, neutrons and superconducting protons interact in the stellar interior, where matter exists in quantum states impossible to study in terrestrial laboratories. The study of neutron star magnetic fields has practical applications for understanding magnetic confinement fusion. The plasma physics governing particle behavior in tokamak fusion reactors involves the same magnetic confinement principles operating around neutron stars, albeit at vastly different scales and field strengths. Neutron star magnetospheres also serve as natural particle accelerators that achieve energies beyond our most powerful machines. The Large Hadron Collider can accelerate protons to 6.5 trillion electron volts. Neutron star magnetic fields routinely accelerate particles to energies exceeding 1,000 trillion electron volts, providing insights into cosmic ray acceleration mechanisms throughout the universe. Understanding how neutron stars maintain such extreme magnetic fields over millions of years reveals fundamental aspects of how magnetic energy gets stored and released in cosmic environments. These stellar magnetic monsters demonstrate that the universe operates magnetic field strengths that push the boundaries of what matter and energy can withstand. As we'll discover next, these intense magnetic fields combine with extreme rotation rates to create cosmic timekeepers more precise than our best atomic clocks, turning neutron stars into natural laboratories for testing the fundamental constants of physics. Chapter 5. Cosmic Clocks. Deep space contains the most precise timekeepers in the known universe, and they're not made by human hands. Neutron stars spinning hundreds of times per second maintain timing accuracy that rivals our best atomic clocks, keeping time with such precision that astronomers use them to detect gravitational waves rippling through space itself. These cosmic metronomes reveal how extreme physics can create clockwork precision from the chaos of stellar death. The story of neutron star timing begins with conservation of angular momentum, the same principle that makes figure skaters spin faster when they pull their arms close to their bodies. When a massive star's core collapses from roughly Earth size down to city size, any rotation gets amplified by the square of the compression ratio. A slowly rotating stellar core becomes a frantically spinning neutron star in less than a second. Dr. Thomas Gold at Cornell University first proposed in 1968 that pulsars were rotating neutron stars, not oscillating white dwarf stars as originally thought. His insight explained how these stellar remnants could generate such precisely timed signals. They were lighthouse beams from spinning magnetic fields, not vibrating stellar surfaces. The fastest known pulsar, PSRJ 1748-2446, located in the globular cluster Terzan 5, spins 716 times per second. At this rotation rate, points on the neutron star's equator travel at 24% the speed of light. Any faster, and centrifugal forces would overcome even nuclear density matter's gravitational binding, tearing the star apart. This rotation rate represents a natural speed limit imposed by the fundamental properties of matter itself. The balance between gravitational attraction and centrifugal force determines the maximum spin rate for neutron stars, providing a direct measurement of how matter behaves under extreme conditions impossible to study in terrestrial laboratories. Pulsar timing achieves precision that surpasses most atomic clocks. The millisecond pulsar PSRJ 1939+2134 maintains timing stability better than 1 part in 1015 over periods of years. This means the pulsar's rotation period changes by less than 1 nanosecond per year, timing precision comparable to the best cesium atomic clocks used to define international time standards. The Arecibo Observatory's pulsar timing program, led by Dr. Joseph Taylor, demonstrated this remarkable precision by tracking pulsar PSRB 1913+16 for decades. Taylor and Russell Hulse discovered that this pulsar's orbit was decaying by exactly the amount predicted by Einstein's theory of general relativity due to energy loss through gravitational wave radiation. This discovery provided the first indirect evidence for gravitational waves, earning Taylor and Hulse the 1993 Nobel Prize in Physics. Their work showed that neutron stars serve as natural laboratories for testing Einstein's most exotic predictions about the nature of space and time. Modern pulsar timing arrays use networks of radio telescopes to monitor dozens of millisecond pulsars simultaneously, creating a galaxy-spanning gravitational wave detector. The North American Nanohertz Observatory for Gravitational Waves, NAONOGRAV, collaboration times 45 pulsars with precision sufficient to detect gravitational waves from supermassive black hole mergers occurring billions of light years away. The timing precision achieved by pulsar observations requires accounting for effects that would be negligible in any other astronomical context. Pulsar signals must be corrected for Earth's orbital motion around the Sun. the solar system's motion through the galaxy, and even the gravitational influence of planets in our solar system. The analysis includes corrections for relativistic effects like time dilation and gravitational redshift. Dr. Ingrid Stairs at the University of British Columbia has shown that pulsar timing can detect the gravitational influence of objects as small as asteroids and distant star systems. The timing precision is so extraordinary that variations in pulse arrival times of just 100 nanoseconds can reveal the presence of planetary mass objects orbiting neutron stars light years away. This precision emerges from the unique physics of neutron-star rotation. Unlike normal stars, which have gaseous surfaces that can exhibit turbulence and variability, neutron stars possess crystalline crusts that rotate as solid bodies. The interior superfluid neutrons and superconducting protons maintain quantum mechanical rigidity that preserves rotational stability over millions of years. Occasionally, neutron stars experience sudden spin-up events called glitches, where the rotation rate increases abruptly by a few parts per million before gradually returning to its previous decline rate. These glitches provide insights into neutron star internal structure, revealing how the superfluid interior couples to the solid crust through quantum mechanical processes. The Vela pulsar, one of the most studied neutron stars, experiences a major glitch approximately every 3 years. During these events, the pulsar's rotation period decreases by about 2 parts per million in less than a day. The subsequent recovery takes weeks to months, suggesting complex interactions between the neutron star's superfluid core and crystalline crust. Neutron star timing precision enables measurements impossible with any other astronomical objects. The double pulsar system PSRJ 073-73039, discovered in 2003, contains 2 neutron stars orbiting each other every 2.4 hours. This system allows astronomers to test general relativity with unprecedented precision by timing both pulsars and comparing their orbital decay predictions. These measurements have confirmed Einstein's predictions for gravitational wave energy loss to better than 0.05% accuracy, the most precise test of general relativity in the strong field regime. The system's orbital parameters change exactly as predicted by Einstein's equations, providing compelling evidence that gravitational waves carry energy away from accelerating masses. International pulsar timing array collaborations use neutron star clocks to search for gravitational wave backgrounds from cosmic string networks, phase transitions in the early universe, and primordial black hole populations. The timing precision achieved by monitoring millisecond pulsars for decades creates sensitivity to gravitational effects that occurred when the universe was less than a second old. The European Pulsar Timing Array recently reported evidence for gravitational wave background signals in their 25-year dataset, potentially the first detection of the cumulative effect of supermassive black hole mergers throughout cosmic history. This discovery demonstrates how neutron star timing precision can reveal processes occurring across the entire observable universe. Perhaps most remarkably, neutron star rotation provides insights into the fundamental nature of time itself. By monitoring pulsars in different gravitational environments, isolated neutron stars, binary systems, and globular clusters, astronomers can test whether time passes uniformly throughout the universe or varies due to local gravitational effects. The timing stability of neutron stars suggests that the fundamental constants of physics, including the fine structure constant and gravitational constant, remain stable over cosmic timescales. Any variation in these constants would show up as systematic changes in pulsar rotation rates, providing tests of unified field theories and cosmological models. Neutron star clocks also serve practical purposes for navigation and timekeeping. NASA has tested X-ray pulsar navigation systems that could provide positioning information for spacecraft in the outer solar system, where GPS signals are unavailable. These systems use X-ray detectors to time pulsar signals and triangulate spacecraft position with accuracy comparable to terrestrial navigation systems. The study of neutron-star timing reveals how extreme physics can produce clockwork precision from gravitational collapse and magnetic field generation. These cosmic timekeepers demonstrate that nature operates with mathematical precision, even in the most violent and extreme environments imaginable. As we'll explore next, this precise timing, combined with neutron-star density and magnetic fields, makes these stellar remnants the universe's most powerful lighthouses, broadcasting signals detectable across thousands of light years with energy outputs that defy easy comprehension. Chapter 6: Pulsar Lighthouses Across the Vastness of Space. Neutron stars sweep beams of radiation so intense they outshine entire galaxies in specific wavelengths of light. These cosmic lighthouses operate on principles so extreme they challenge our understanding of how matter and energy interact under conditions that exist nowhere else in the universe. Every 1.337 seconds, the first discovered pulsar sends a flash of radio waves toward Earth with the punctuality of an atomic clock, demonstrating how stellar death creates the most powerful beacons in the cosmos. The lighthouse mechanism begins with the neutron star's magnetic field, which traps charged particles and accelerates them to velocities approaching the speed of light. These particles spiral along magnetic field lines, radiating energy in tightly focused beams that sweep through space like searchlights as the neutron star rotates. When these beams point toward Earth, radio telescopes detect brief pulses of radiation lasting just milliseconds. Dr. Anthony Hewish and his student Jocelyn Bell Burnell discovered this phenomenon almost by accident in 1967 while using a new radio telescope to study quasars. The regular signals they detected initially seemed so artificial that the Cambridge research team half-seriously considered the possibility of alien communications, temporarily labeling the source LGM-1 for Little Green Men. What they had actually found was far stranger than alien technology: a stellar corpse with a magnetic field 1 trillion times stronger than Earth, spinning 30 times per second while broadcasting radio waves across interstellar distances. The precision of these signals, varying by less than 1 part in 10 million, revealed a cosmic phenomenon operating with clockwork accuracy, despite being born from one of the most violent explosions in the universe. The energy requirements for pulsar radiation defy easy comprehension. The Crab pulsar, formed by a supernova witnessed by Chinese astronomers in 1054 AD, broadcasts more energy every second than our Sun produces in an entire day. This energy comes from the neutron star's rotation, which gradually slows down as magnetic field interactions convert rotational kinetic energy into radiation. To understand how neutron stars generate such powerful beams, imagine a cosmic particle accelerator the size of Manhattan. The neutron star's magnetic field creates electric fields strong enough to strip electrons from any nearby atoms and accelerate them to energies exceeding what we can achieve in our most powerful terrestrial machines. These accelerated particles then radiate energy across the electromagnetic spectrum, from radio waves to gamma rays. The Fermi Gamma Ray Space Telescope has revealed that young pulsars like the Crab emit most of their energy as gamma rays, the highest energy form of electromagnetic radiation. Each gamma ray photon from the Crab pulsar carries millions of times more energy than visible light photons, yet the neutron star produces billions of these high-energy particles every second. Dr. Alice Harding at NASA's Goddard Space Flight Center has developed models showing how pulsar magnetospheres create natural particle accelerators more powerful than anything humans have built. The electric fields generated by rotating magnetic field lines in the neutron star's magnetosphere can accelerate particles to energies exceeding 1,000 trillion electron volts, energies that probe the fundamental structure of matter itself. Recent observations from the Very Large Array Radio Telescope have revealed pulsar emission mechanisms of extraordinary complexity. The emission regions where particles generate radio waves exist hundreds of kilometers above the neutron-star surface, in zones where magnetic field strength exceeds Earth's field by factors of trillions. These regions channel particle beams with precision that would be impossible to achieve artificially. The lighthouse beam pattern isn't random. It is determined by the neutron-star's magnetic field geometry. Computer simulations show that magnetic field lines emerge from the neutron-star's magnetic poles and extend into space, creating funnel-shaped emission regions. As the neutron star rotates, these emission funnels sweep across space like lighthouse beams, creating the periodic signals we detect as pulses. Not all neutron stars appear as pulsars from Earth. The lighthouse beam pattern means we can only detect neutron stars whose emission beams happen to point toward our solar system during their rotation. Astronomers estimate that for every pulsar we observe, there are roughly 6 neutron stars whose beams miss Earth entirely, hidden in the darkness of space. The Parkes Observatory in Australia has discovered over 1,000 pulsars using sensitive radio receivers that can detect signals weaker than the energy needed to power a digital watch. These discoveries reveal a galaxy populated with thousands of cosmic lighthouses, each operating with its own characteristic pulse period and emission pattern. Some pulsars operate as double lighthouses, with emission beams from both magnetic poles visible as the neutron star rotates. The double pulsar system PSRJ 07373039 allows astronomers to observe both neutron stars in a binary system, providing unprecedented insights into how these cosmic lighthouses interact gravitationally and electromagnetically. Millisecond pulsars represent the ultimate evolution of cosmic lighthouses. These ancient neutron stars have been spun up to rotation rates exceeding 700 revolutions per second through matter accretion from companion stars. Despite their advanced age, these rapidly rotating lighthouses maintain timing precision that surpasses our best atomic clocks. The lighthouse mechanism operates across multiple wavelengths simultaneously. While radio waves provide the most easily detected signals, pulsars also emit optical light, X-rays, and gamma rays in synchronized beams. The Hubble Space Telescope has captured visible light from pulsar lighthouse beams, revealing optical emissions synchronized with radio pulses detected by ground-based telescopes. Dr. Victoria Caspi of McGill University has led studies of magnetar lighthouses, neutron stars with magnetic fields so intense they occasionally produce gamma-ray bursts visible across the observable universe. These stellar lighthouses operate in an extreme regime where magnetic energy dominates all other forces, creating emission mechanisms that exist nowhere else in nature. The energy efficiency of pulsar lighthouses approaches theoretical limits. Computer models show that rotating neutron stars convert rotational energy into radiation with efficiency exceeding 99%, far superior to any artificial light source. This efficiency emerges from the perfect coupling between magnetic field rotation and particle acceleration. In the neutron star as magnetosphere, pulsar lighthouse beams carry encoded information about neutron star interior structure. The precise timing of radio pulses reveals how matter behaves at nuclear density, while pulse polarization patterns provide insights into magnetic field geometry. Each lighthouse beam serves as a probe of physics operating under conditions impossible to study in terrestrial laboratories. The discovery of fast radio bursts, REEF, intense flashes of radio waves from distant galaxies, has revealed a new class of cosmic lighthouses. While their exact nature remains mysterious, some theories suggest they originate from magnetar flares or neutron-star collisions, representing the most extreme lighthouse phenomena in the universe. International collaborations now use networks of radio telescopes to create virtual lighthouse detectors spanning continents. The European VLBI network can combine signals from telescopes across Europe and Asia, achieving resolution capable of measuring lighthouse beam patterns with precision equivalent to reading newspaper text on the moon's surface. Perhaps most remarkably, pulsar lighthouses serve as cosmic GPS beacons for interstellar navigation. NASA has successfully tested X-ray pulsar navigation systems that use lighthouse timing signals to determine spacecraft position in the outer solar system. These cosmic beacons provide navigation references that will remain stable for millions of years. The study of neutron-star lighthouses reveals how extreme physics creates the most powerful and precise signaling systems in the universe. These cosmic beacons demonstrate that stellar death doesn't represent an ending, but a transformation into something far more exotic and energetic than the original star. Understanding pulsar lighthouse mechanisms also provides insights into how the universe will look in the far future when normal stars have burned out, and neutron-star lighthouses may be among the last active sources of electromagnetic radiation in a cold, dark cosmos. As we'll discover next, these cosmic lighthouses occasionally fail catastrophically, producing explosions so violent they briefly outshine entire galaxies and forge the heaviest elements in the universe. Chapter 7. Stellar explosions. When neutron stars reach the breaking point, they produce the most violent explosions since the Big Bang. These cosmic detonations release more energy in seconds than our Sun will generate throughout its entire 10 billion year lifetime, creating temperatures exceeding 100 billion degrees and forging elements that cannot be created anywhere else in the universe. The story of neutron star explosions reveals how stellar death becomes cosmic rebirth on scales that dwarf human comprehension. The most spectacular neutron star explosions occur when two of these dense stellar remnants spiral into each other in a cosmic dance of destruction. As they orbit ever closer, losing energy to gravitational wave radiation, tidal forces begin tearing apart their surfaces. Material ripped from neutron star crusts forms an accretion disk of matter heated to temperatures where atomic nuclei fuse into the heaviest elements in the periodic table. Dr. Brian Metzger at Columbia University first calculated the energy release from neutron star mergers in the early 2000s, predicting explosions that would briefly outshine entire galaxies. His model showed that colliding neutron stars would create a kilonova, an explosion 1,000 times brighter than ordinary supernova, powered not by nuclear fusion, but by the radioactive decay of newly formed heavy elements. On August 17, 2017, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from two neutron stars merging 130 million light-years away. The collision, designated GW1-70817, marked the first time astronomers observed the same event in both gravitational waves and electromagnetic radiation, opening an entirely new window into the universe's most extreme physics. The merger sequence lasted just 100 seconds from initial detection to final explosion, but the energy released defied comprehension. During the final moments before collision, the two neutron stars orbited each times per second, generating gravitational waves that carried away energy equivalent to converting 3 solar masses into pure radiation. The space-time distortions reached Earth as ripples measuring 1/10,000th the width of a proton. When the neutron stars finally touched, their surfaces collided at 30% the speed of light. The impact generated temperatures exceeding 100 billion degrees, hot enough to photodisintegrate atomic nuclei back into individual protons and neutrons. For a brief moment, conditions in the collision zone resembled the universe's first microseconds after the Big Bang. The explosion ejected roughly 1/10 of a solar mass in heavy elements into space. Spectroscopic observations revealed the formation of gold, platinum, uranium, and other elements heavier than iron that cannot be produced in ordinary stellar cores. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all were likely forged in neutron-star collisions like this one. Dr. Ido Berger's team at Harvard used the Hubble Space Telescope to track the kilonova's optical afterglow for months after the initial explosion. Their observations confirmed theoretical predictions that neutron-star mergers create raw process elements through rapid neutron capture, a nuclear process that builds heavy elements faster than they can radioactively decay. But neutron-star mergers represent just one type of stellar explosion. Individual neutron stars can explode catastrophically when their magnetic fields become unstable. Magnetars neutron stars with the strongest magnetic fields in the universe occasionally undergo magnetic field reconfigurations that release energy equivalent to thousands of hydrogen bombs, detonating every second for hours. The most powerful magnetar explosion ever recorded occurred on December 27, 2004, when SGR 1806-20 released more energy in 1/10 of a second than our Sun produces in 250,000 years. The gamma-ray burst temporarily saturated detectors throughout the solar system and disrupted radio communications on Earth's night side, despite originating 50,000 light-years away. These magnetar explosions occur when magnetic stress exceeds the structural strength of matter at nuclear density. Computer simulations show that magnetic fields approaching 1,000 trillion Gauss can literally crack neutron star crusts, causing massive starquakes that release stored magnetic energy instantaneously. The resulting gamma-ray bursts represent the brightest electromagnetic phenomena in the universe. NASA's Swift gamma-ray burst mission has detected magnetar explosions from across the Milky Way galaxy. Some of these bursts repeat irregularly over years or decades, suggesting that neutron star crusts can undergo multiple fractures as magnetic fields continue evolving. Each explosion provides insights into how matter behaves under conditions more extreme than anything achievable in terrestrial laboratories. Neutron stars can also explode through thermonuclear processes when they accrete matter from companion stars. As hydrogen accumulates on the neutron star surface, temperatures and pressures eventually trigger helium flash explosions, thermonuclear detonations that briefly increase the neutron star's luminosity by factors of thousands. These Type 1 X-ray bursts occur every few hours to days on accreting neutron stars, creating conditions where nuclear burning becomes unstable. The explosions consume accumulated hydrogen and helium in seconds, generating temperatures exceeding 1 billion degrees and creating nuclear ash that settles back onto the neutron star surface. Dr. Zhang Intezand at the Netherlands Institute for Space Research has used the Rossi X-ray Timing Explorer to study hundreds of these thermonuclear explosions. His observations revealed that neutron star surface explosions follow complex patterns determined by accretion rates, stellar magnetic fields, and nuclear physics operating under extreme conditions. Some neutron stars undergo even more exotic explosions when accumulated matter reaches critical density for electron capture. These explosions occur when the neutron star's gravitational field becomes strong enough to force electrons into protons, creating additional neutrons and releasing enormous amounts of neutrino radiation. The most extreme neutron star explosions may occur when these stellar remnants exceed the Tolman-Oppenheimer-Volkoff limit, the maximum mass that neutron star matter can support against gravitational collapse. When neutron stars grow beyond approximately 2.16 solar masses through accretion or mergers, even nuclear forces cannot prevent further collapse into black holes. Recent gravitational wave observations suggest that some neutron star mergers create black holes directly, while others form hypermassive neutron stars that survive for milliseconds before collapsing. These transitions represent the most extreme stellar explosions possible, events where matter itself surrenders to gravity and disappears behind event horizons. The Chandra X-ray Observatory has observed the aftermath of neutron star explosions in supernova remnants like Cassiopeia A, where a neutron star formed 300 years ago continues heating surrounding material to temperatures exceeding 30 million degrees. These observations reveal how stellar explosions distribute heavy elements throughout space and trigger the formation of new generations of stars and planets. Neutron star explosions also serve as cosmic particle accelerators, generating cosmic rays with energies exceeding what we can produce in our most powerful machines. The shock waves from these explosions accelerate protons and atomic nuclei to speeds approaching the speed of light, creating the highest energy particles in the universe. Dr. Felix Aharonyan's team at the Max Planck Institute has used gamma-ray telescopes to study how neutron star explosions create these extreme cosmic rays. Their observations reveal acceleration mechanisms operating at efficiencies impossible to achieve artificially, providing insights into fundamental processes governing particle physics under extreme conditions. Perhaps most remarkably, neutron star explosions operate as cosmic element factories that make complex chemistry and biology possible. Without the heavy elements forged in these stellar explosions, planets like Earth could not exist. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar explosions and distributed by neutron star mergers. The study of neutron star explosions reveals how stellar death drives cosmic evolution. These violent events don't represent endings, but transformations that enrich the universe with heavy elements, trigger new star formation, and create the chemical diversity necessary for planetary systems and life itself. Understanding neutron star explosions also provides insights into the universe's future. As normal star formation gradually declines over cosmic timescales, neutron star mergers may become the dominant sources of heavy element production, determining the chemical evolution of galaxies billions of years from now. As we'll explore next, the extreme physics governing neutron star explosions creates natural laboratories where matter reaches states impossible to study anywhere else, revealing fundamental properties of nuclear physics and quantum mechanics. Chapter 8. Laboratory Physics. Neutron stars serve as the universe's most extreme physics laboratories, creating conditions impossible to replicate on Earth where matter reaches densities that dwarf atomic nuclei and temperatures that melt the fundamental structure of reality itself. Every measurement we make of these stellar remnants provides insights into physics regimes that our most powerful particle accelerators cannot approach, revealing how nature operates when pushed beyond all familiar limits. To understand why neutron stars represent such extraordinary laboratories, consider the extreme conditions they contain. Surface gravities 200 billion times stronger than Earth's create pressures that would compress diamond into a fluid. Magnetic fields trillions of times more intense than anything achievable on Earth restructure atomic orbitals and force matter into quantum states that exist nowhere else in the universe. The interior of a neutron star contains matter at densities 5 to 10 times greater than atomic nuclei. At these densities, the very concept of individual atoms breaks down. Protons and electrons get crushed together to form neutrons, creating a quantum fluid of nuclear matter that exhibits properties impossible to study in terrestrial laboratories. Dr. Gordon Bain at the University of Illinois pioneered theoretical studies of neutron star matter in the 1970s, showing that these stellar laboratories contain phases of matter that exist nowhere else. The transition from normal atomic matter to neutron star matter represents one of the most extreme phase transitions in physics, comparable to the conditions that existed in the universe's first microseconds after the Big Bang. Computer simulations reveal that neutron star interiors may contain exotic forms of matter, including Hyperion gases, kaon condensates, and quark matter, phases that can only exist under pressures exceeding what we can create in particle accelerators. These exotic matter phases could explain why neutron stars are more massive than theoretical models initially predicted. The neutron-star interior composition explorer, NICER, on the International Space Station uses X-ray timing measurements to probe neutron-star internal structure with unprecedented precision. By measuring how X-rays from hotspots on neutron-star surfaces are bent by intense gravitational fields, NICER can determine neutron-star radii to within a few hundred meters across distances of thousands of light years. These measurements provide direct tests of nuclear physics theories that describe how matter behaves at densities exceeding atomic nuclei. The relationship between neutron star mass and radius constrains the equation of state for nuclear matter, the fundamental relationship between pressure, density, and energy that governs matter under extreme conditions. Recent NICER observations of pulsar PSRJ 0030+0451 revealed that neutron star matter is stiffer than many theoretical models predicted, suggesting that exotic matter phases may not appear until densities exceed 5 times nuclear density. These measurements represent the first direct constraints on nuclear physics from astronomical observations. Neutron stars also serve as laboratories for testing Einstein's theory of general relativity under conditions impossible to achieve artificially. The double pulsar system PSRJ 07373039 allows astronomers to test gravitational effects with precision exceeding laboratory experiments by factors of millions. Measurements of orbital decay due to gravitational wave energy loss confirm Einstein's predictions to better than 0.05% accuracy. Dr. Ingrid Stairs at the University of British Columbia has used pulsar timing measurements to test whether gravitational interactions depend on the internal structure of the interacting masses. These tests of the strong equivalence principle probe fundamental assumptions about gravity using neutron star laboratories, where gravitational binding energy represents 10 to 20% of the total mass. The extreme magnetic fields around neutron stars create natural laboratories for studying quantum electrodynamics under conditions impossible to replicate on Earth. In magnetic fields exceeding 100 million times Earth's field, the quantum vacuum itself becomes polarized, creating effects where empty space behaves like an optical medium with refractive properties. European Southern Observatory telescopes have detected polarized light from neutron star magnetospheres, providing evidence for vacuum polarization effects predicted by quantum field theory. These observations confirm that intense magnetic fields can make empty space behave like matter, demonstrating quantum mechanical effects on macroscopic scales. Neutron star surfaces serve as laboratories for studying matter under extreme gravitational redshift. Light escaping from neutron star surfaces loses about 30% of its energy climbing out of the gravitational well, providing direct measurements of how gravity affects electromagnetic radiation. These natural experiments test fundamental relationships between matter, energy, and spacetime curvature. The timing precision of millisecond pulsars creates laboratories for testing the stability of fundamental constants over cosmic timescales. Any variation in the fine structure constant, gravitational constant, or other fundamental parameters would appear as systematic changes in pulsar rotation rates. Decades of pulsar timing data show that these constants remain stable to better than 1 part in 1016 per year. Dr. Andrea Lohman at Franklin and Marshall College leads efforts to use pulsar timing arrays as gravitational wave detectors, creating laboratories that span our galaxy. These networks of precisely timed neutron stars can detect gravitational waves from supermassive black hole mergers, cosmic string networks, and possibly even relics from cosmic inflation in the early universe. Neutron star mergers observed through gravitational waves create laboratories for studying matter under the most extreme conditions since the Big Bang. The collision GW170817 revealed how matter behaves when accelerated to significant fractions of light speed under gravitational fields that curve spacetime into nearly closed loops. These merger events also serve as laboratories for studying or process nucleosynthesis, the rapid neutron capture process that creates elements heavier than iron. Spectroscopic observations of kilonova emissions provide direct evidence for heavy element formation under conditions impossible to replicate in any terrestrial facility. The study of neutron-star cooling provides laboratories for testing theories of exotic matter and fundamental particle physics. Young neutron stars cool primarily through neutrino emission, and the cooling rate depends sensitively on the types of exotic particles that might exist in neutron star cores. Observations of neutron star temperatures constrain theories of beyond standard model physics. NASA's Chandra and Zuras Ray Observatory has measured surface temperatures of neutron stars with ages ranging from hundreds to millions of years, providing data on how these stellar laboratories cool over cosmic timescales. The cooling curves reveal information about neutron star internal structure and the properties of matter at supernuclear densities. Perhaps most remarkably, neutron stars serve as laboratories for studying matter that may not exist anywhere else in the universe. The extreme conditions in neutron star cores may create quark matter, color superconducting phases, or other exotic states predicted by quantum chromodynamics but never observed directly. Dr. Madhapa Prakash at Ohio University has developed theoretical models showing that neutron star cores may undergo phase transitions to quark matter at densities exceeding 6 times nuclear density. These phase transitions would affect neutron star cooling, rotation, and gravitational wave emission in ways that could be detected by current and future observatories. The magnetic field evolution of neutron stars provides laboratories for studying superconductivity and superfluidity under extreme conditions. The interior of neutron stars contains superconducting protons and superfluid neutrons that maintain quantum coherence over astronomical length scales. Understanding these quantum states helps explain how neutron stars maintain their magnetic fields for millions of years. Northern star glitches, sudden spin-up events, serve as laboratories for studying the interaction between superfluid and normal matter under extreme conditions. These events reveal how quantum vortices and superfluid neutrons couple to the neutron star's crystalline crust, providing insights into quantum mechanical processes operating on macroscopic scales. International collaborations now use neutron star observations to constrain fundamental physics in ways impossible with terrestrial experiments. The European Gravitational Observatory's Virgo detector, combined with LIGO observations, has created a network of laboratories spanning multiple continents to study how matter behaves under the most extreme conditions in the universe. The study of neutron stars as physics laboratories reveals how nature creates conditions that probe the fundamental limits of matter, energy, and spacetime. These stellar remnants demonstrate that the universe operates regimes of physics far beyond our everyday experience, where quantum mechanics and general relativity merge into unified descriptions of reality. Understanding neutron star physics also has practical applications for terrestrial technology. The superconducting and superfluid states that exist in neutron star interiors inspire research into room temperature superconductors and quantum computing systems. The extreme precision of pulsar timing informs the development of next-generation atomic clocks and navigation systems. As we'll discover next, neutron stars don't just serve as laboratories for studying known physics. They may be factories for creating entirely new forms of matter that challenge our understanding of what is possible in the universe.